Hi again, this is Andy, K4GKP, and welcome back to the Ham Whisperer and lesson 24 in the General Class Operator Element 3 exam. In this lesson we go over the G6B questions from the General Class question pool. The G6B section of questions goes over rectifiers, solid-state diodes and transistors, solar cells, vacuum tubes, and batteries. What is the peak inverse voltage rating of a rectifier? Well, the answer is the maximum voltage the rectifier will handle in the non-conducting direction. Now, there's a little bit of review, but you have to remember a rectifier is essentially a diode, and they only allow current to flow in one direction. So the conducting direction is the direction the rectifier will allow the current to flow. The non-conducting direction is the direction the rectifier will block the current. So the rectifier's ability to allow current to only flow in one direction is not absolute. So if you apply enough voltage in the non-conducting direction, you can break through or overcome the diode or the rectifier's ability to block current in that direction. So if you apply enough voltage, current will flow in the wrong direction, and when this happens, it's usually the end of that rectifier. So the peak inverse voltage is the maximum amount of voltage a rectifier can handle before this breakdown and current will flow in the non-conductive direction. What are the two major ratings that must not be exceeded for silicon-diode rectifiers? All right, the two ratings are peak inverse voltage and average forward current. So peak inverse voltage we already talked about in the last question. A very untechnical explanation for average forward power is the amount of power that can be applied to a rectifier before it overheats and breaks. So the peak inverse voltage is what you should probably focus on to sort this question out from the others. It's not an obvious the correct answer isn't obvious and doesn't stand out too well from the other answers, minus the peak inverse voltage part of it, which we've already talked about in the last question. What is the approximate junction threshold voltage of a germanium diode? The answer is 0.3 volts. Now, the junction threshold voltage is the voltage it takes to get the current to flow across the PN junction of a germanium diode. And remember, semiconductors aren't very good conductors, but they're not very good insulators, so they're kind of in between. So to get current to flow across semiconductor material, you need kind of a little bit more of a push than with a good conductor. So for a germanium diode, that push is 0.3 volts. So basically, in order for the diode to function, you need at least 0.3 volts of force. So this is one you probably need to memorize. When two or more diodes are connected in parallel to increase current handling capacity, what is the purpose of the resistor connected in series with the diode? All right, the resistors ensure that the diode doesn't carry most of the current. So the resistors are put in place just before each of the diodes, and this builds off of the junction threshold voltage question from the last question. Sometimes differences in the junction threshold voltages in the two diodes can direct more voltage to one diode than the other, or more current to one diode than the other. And the resistors help avoid this. So it kind of evens the resistance, if you want to talk about it that way, between the two diodes so that each diode gets an equal amount of power going to it. So the resistors ensure that one diode doesn't carry most of the current. What is the approximate junction threshold voltage of a silicon diode? All right, this same type of question as the germanium diode question, but for silicon diode, it's 0.7 volts. So this is another one to memorize. The junction threshold voltage of a silicon diode is 0.7 volts. So in order to get a silicon diode to function, you need at least 0.7 volts of force. Which of the following is an advantage of using a Schottky diode in an RF switching circuit as compared to a standard silicon diode? The answer is low capacitance. And we talked about this a little bit in the previous lesson, where sometimes electrical components behave like other electrical components based on some deficiencies in their design. Now, when current diodes have this problem too. So when current to a diode switches direction, a little bit of capacitance builds up across the depletion region. So essentially the P and the N material end up acting a little bit like a capacitor. A Schottky diode has a small piece of gold or platinum built in it, which helps to dissipate the capacitance charge, thus lowering the capacitance. So basically it helps dissipate the electric field. If you can remember that diodes can have capacitance issues, the correct answer is the only one dealing with capacitance. So the advantage of a Schottky diode compared to a silicon diode is lower capacitance. What are the stable operating points for a bipolar transistor that is used as a switch in a logic circuit? The answer is its saturation and cutoff regions, and takes a little bit of explanation. So we already know that a transistor can perform a whole bunch of different functions. They're switches, they're amplifiers, they control current, all that stuff. So the current polarity, so what the polarity, whether it's plus or minus, is applied, and the amount of voltage that's applied to a transistor's various electrodes impact the size and effectiveness of the depletion regions created at the various semiconductor junctions. So, the depletion region between the P and the N junction. The transistor is either wide open, completely closed, or somewhere in the middle. And these various states are referred to as regions. So the saturation region in a transistor is when the transistor is allowing current to flow freely through it, so all the way on. The cutoff region is a complete shutdown of current, so the depletion region is blocking all the current going through the transistor. And the in-between is called the active region. So with a switch, you either want the current all the way on or you want the current all the way off. So therefore, if a transistor is acting as a switch, you want either the saturation region or the cutoff region to be the two regions that you're working in. Now, the active region kind of defeats the purpose of a switch because it's allowing current to flow, which isn't all the way on or off. Why is it often necessary to insulate the case of a large power transistor? The answer is to avoid shorting the collector or drain voltage to ground. And this one also requires a bit of explanation. And one thing you've got to remember is that transistors, the leads on various different transistors have different names. And when we're talking drain and ground, we're talking about transistor leads. So when you deal with large amounts of power, a transistor can heat up pretty quickly. So to help dissipate the heat, sometimes a transistor's collector or drain may be connected to the case so that it can act as a heat sink. So essentially, two leads from the transistor are hooked up to the case to dissipate the heat. The problem is cases are often used as grounds, and the collector and drain of a transistor are not usually grounded. So therefore, the case that you're using as a heat sink would need to be insulated to prevent any inadvertent grounding. So it's a little bit deep, but I hope you get it. Which of the following describes the construction of a MOSFET? The answer is the gate is separated from the channel with a thin insulating layer. And all right, a MOSFET is a type of transistor, and it stands for metal oxide semiconductor field effect transistor. And the big deal with a MOSFET is that the gate electrode does not make direct contact with the semiconductor material. The gate is insulated by a thin layer of oxidized metal or oxidized material between the gate and the semiconductor material, which is the metal oxide part of MOSFET. So essentially, it just doesn't make contact. And of all the possible answers, the gate being separated from the channel with a thin insulating layer is the one that fits the description of a MOSFET construction the best. Which element of a triode vacuum tube is used to regulate the flow of electrons between cathode and plate? And the answer is the control grid. And this one also, unless you're familiar with vacuum tubes, this one's going to take a little bit of explanation as well. A triode vacuum tube is a vacuum tube which contains a cathode, a grid, and a plate. So if you imagine a vacuum tube is sort of like a transistor, it's got different leads as well. And so a triode has a cathode, a grid, and a plate. The triodes are usually used to amplify signals, and this works similar to a field effect transistor. In a triode vacuum tube, current flows from the cathode to the plate through a mesh of wires called the control grid. Now, if a negative charge is applied to the control grid, it repels the electrons flow from the cathode to the plate, which stops the current. If a positive charge is applied to the control grid, it pushes electrons through, amplifying the current. So the element of a triode that is used to regulate the flow of electrons between cathode and plate is the control grid. Which of the following solid-state devices is most like a vacuum tube in its general characteristics? And the answer is a FET. A field effect transistor is, and we talked about this a little bit in the previous question, is most like a vacuum tube in its general characteristics. So like the triode vacuum tube, a FET has three leads, or electrodes. The triode has the cathode, the plate, and the control grid. The FET has the source, the drain, and the gate. Now, the control grid in the vacuum tube and the gate in the FET serve essentially the same purpose in controlling the current through the transistor of the vacuum tube. And this is a tricky one on the exam. None of the answers will jump out as obviously correct. So one of the correct possibilities is a bipolar transistor, which is not the correct answer. You want the best answer, and the best answer for this question is field effect transistor. What is the primary purpose of a screen grid in a vacuum tube? The answer is to reduce grid-to-plate capacitance. So apparently capacitance is everywhere because we've talked about it a whole bunch, and it's a problem with transistors, vacuum tubes, and etc. The screen grid is another piece of a vacuum tube, and what it does is it basically helps negate the capacitance between the grid and the plate in a vacuum tube. So to reduce the capacitance, the screen grid is placed between the control grid and the plate, and it's given a pretty much a constant charge, and that charge basically helps to dissipate the electric field that's built up between those two, the grid and the plate. So the purpose of a screen grid in a vacuum tube is to reduce grid-to-plate capacitance. What is an advantage of the low internal resistance of nickel cadmium batteries? And the answer is high discharge current. And this one you might want to actually memorize unless you're very familiar with NiCad batteries. So nickel cadmium, otherwise known as NiCads, are used for basically things that need a high amount of current. And they're rechargeable and they're pretty handy to have. So the advantage of a nickel cadmium battery is the high discharge current. What is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery? The answer is 10.5 volts, and this one is a lot simpler than the question makes it sound. What the question is asking is how close to dead can you run a battery or a lead acid battery before it seriously starts to degrade the life of the battery? And the answer is 10.5 volts. So if you have a 12-volt car battery, you can discharge it to the point where it only generates 10.5 volts before you really need to recharge it if you want that battery to last a long time. So the minimum allowable discharge voltage in order to maximize the lifespan of a 12-volt lead acid battery is 10.5 volts. When is it acceptable to recharge a carbon-zinc primary cell? This is a simple one. The answer is never. Now, if you remember some review from the technician exam and some stuff from the general class exam, a carbon-zinc battery is a disposable battery. It's what you get at Radio Shack or Walmart or wherever. You stick in a toy, you use it, it's dead, you throw it out. Now, carbon-zinc batteries, like I said, are disposable, and there's really no way to charge them. The way they're made and their chemical composition is not a rechargeable, isn't capable of recharging. So trying to recharge them will just have, basically acid goo leak out of the battery and it'll destroy whatever it touches. So it is never acceptable to recharge a carbon-zinc primary cell. Which of the following is a rechargeable battery? Of all the possible choices, the one on there is the nickel metal hydride. And you already know that the NiCad or nickel cadmium batteries are rechargeable. So are nickel metal hydride or NiMH batteries. So if you can remember the NiCads or nickel cadmium batteries are rechargeable, the nickel metal hydride is the only possible answer on the exam that's got a nickel component. So that's a little memory trick to help you remember this one, or otherwise you're just going to have to memorize the question flat out. And that's the end of the G6B review, and it's time for the G6B quiz. So take out a pen and a piece of paper and number from 1 to 16. I'm going to go through the questions pretty quickly, so if you need more time, just pause the video, take all the time you need. When you're done with the exam, or the quiz rather, you can go to hamwhisper.com and check your answers. You can find it under the exam answers page under the G6B section of questions. So now that you're ready for the quiz, let's get started. Question 1. What is the peak inverse voltage rating of a rectifier? A, the maximum voltage the rectifier will handle in the conducting direction. B, 1.4 times the AC frequency. C, the maximum voltage the rectifier will handle in the non-conductive direction. Or D, 2.8 times the AC frequency. Question 2. What are the two major ratings that must not be exceeded for silicon-diode rectifiers? A, peak inverse voltage and average forward current. B, average power, average voltage, C, capacitive reactance, avalanche voltage, or D, peak load impedance and peak voltage. Question 3. What is the approximate junction threshold voltage of a germanium diode? A, 0.1 volt, B, 0.3 volts, C, 0.7 volts, or D, 1 volt. Question 4. When two or more diodes are connected in parallel to increase current handling capacity, what is the purpose of the resistor connected in series with each diode? A, the resistors ensure the thermal stability of the power supply. B, the resistors regulate the power supply output voltage. C, the resistors ensure that one diode doesn't carry most of the current. Or D, the resistors act as swamping resistors in the circuit. Question 5. What is the approximate junction threshold voltage of a silicon diode? A, 0.1 volt, B, 0.3 volts, C, 0.7 volts, or D, 1 volt. Question 6. Which of the following is an advantage of using a Schottky diode in an RF switching circuit as compared to a standard silicon diode? A, low capacitance, B, lower inductance, C, longer switching times, or D, higher breakdown voltage. Question 7. What are the stable operating points for a bipolar transistor that is used as a switch in a logic circuit? A, its saturation and cutoff regions, B, its active region between the cutoff and saturation regions, C, between its peak and valley current points, or D, between its enhancement and deletion modes. Question 8. Why is it often necessary to insulate the case of a large power transistor? A, to increase the beta of the transistor, B, to improve the power dissipation capability, C, to reduce stray capacitance, or D, to avoid shorting the collector or drain voltage to ground. Question 9. Which of the following describes the construction of a MOSFET? A, the gate is formed by a back-biased junction. B, the gate is separated from the channel with a thin insulating layer. C, the source is separated from the drain by a thin insulating layer. Or D, the source is formed by depositing metal on silicon. Question 10. Which element of a triode vacuum tube is used to regulate the flow of electrons between cathode and plate? A, control grid, B, heater, C, screen grid, or D, suppressor grid. Question 11. Which of the following solid-state devices is most like a vacuum tube in its general characteristics? A, a bipolar transistor, B, an FET, C, a tunnel diode, or D, a varistor. Question 12. What is the primary purpose of a screen grid in a vacuum tube? A, to reduce grid-to-plate capacitance, B, to increase efficiency, C, to increase the high-frequency response, or D, to decrease plate resistance. Question 13. What is an advantage of the low internal resistance of nickel cadmium batteries? A, long life, B, high discharge current, C, high voltage, or D, rapid recharge. Question 14. What is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery? A, 6 volts, B, 8.5 volts, C, 10.5 volts, or D, 12 volts. Question 15. When is it acceptable to recharge a carbon-zinc primary cell? A, as long as the voltage has not been allowed to drop below 1 volt. B, when the cell is kept warm during the recharging period. C, when a constant current charger is used. Or D, never. And question 16. Which of the following is a rechargeable battery? A, carbon-zinc, B, silver oxide, C, nickel metal hydride, or D, mercury. And that's it for the quiz in Lesson 24. Now that you're done with the quiz, stop by hamwhisper.com, check your answers. You can find them under the exam answers page under the G6B section of questions. And until next time, this is Andy, K4GKP, saying 73, and I hope to hear you on the air soon.